Alright, hello class. In this video, we are going to move on to 2.4. However, there's one little thing I wanted to show in 2.3 that is actually extremely useful. This is one of those things, I don't know if I think a lot of people might overlook it if they were just reading through the book, for example. Kind of easy to overlook. So this comes from exercise 2.3.10, and it's one of those that asks you to give a short proof or provide a counterexample. We have this statement here that if the sequence AN converges to 0, and the absolute value of Bn minus B is less than or equal to AN for all n in the naturals, then Bn converges to B. Okay, so what this idea is basically saying is that, okay, if I can get this distance between Bn and B to always be less than A sub n, and that A sub n is converging to 0, that means as n goes out, this distance between Bn and B is getting closer and closer to 0. So eventually, that distance converges to 0, right? So this here is basically saying that this distance between Bn and B itself is going to 0, which is what we're saying is equivalent to saying that Bn converges to B. Okay, so proving this is actually not that tricky, honestly, right? So I'm going to let epsilon be greater than 0. Let me write my proof statement here. I'm going to let epsilon be greater than 0. Now, since AN converges to 0, there exists a capital N such that the absolute value of AN, you say minus 0, okay, is less than epsilon for n, little n, greater than or equal to big N. Now I do want to notice we have not specified that the ANs here are positive, except it's given implicitly here. If every AN is greater than or equal to an absolute value, then they are implicitly positive, or at least non-negative. Okay, so we don't actually need to worry about the absolute value here. So what this actually gives us is, this implies that AN is less than epsilon for n greater than or equal to this capital N. All right, so for all little n greater than or equal to this big N, the absolute value of Bn minus B, well, we know that that's less than or equal to AN by hypothesis. And we know this is less than epsilon since we're looking at little n's greater than this big N. And there we go, which implies Bn converges to B. All right, now here's why this is nice, okay? It's because it lets us bypass the epsilon thing. So for example, let's say we want to prove that the sequence, let's say xn, which equals let's say n over 2n plus 4, I want to prove that that converges to 1/2. Now up until this point, we've basically we've basically used an epsilon definition, or yeah, the epsilon way of doing it, like we did up here. But I want to show that we can actually use this exercise from the book, this exercise 2.3.10, in the following way. So notice, or I'll just say note, for all n, I'll just say all n in the naturals, we have that the absolute value of n over 2n plus 4 minus 1/2, and now I'm just going to do a bunch of algebra. All right, so n over 2n plus 4 minus 1/2, that's going to be 2n minus 2n minus 4 on the numerator, and 2n plus 4 times 2 on the denominator. Now, you know, this pretty much simplifies a lot. The two n's cancel, and so we're left with, and we can factor, let's say, a 2 out of here, so I'm left with -1 all over, let's say, 4 times n plus 2. All right, and then since we're taking the absolute value, well, first of all, the 4's cancel, and then the absolute value will take care of that negative. So we get down to that this is basically just equal to 1 over n plus 2. Now, n plus 2, I know, is less than 1 over n. Okay, and 1 over n, so 1 over n goes to 0, and we just showed that the absolute value of x sub n minus 1/2 is less than 1 over n for all n in the naturals, so xn converges to 1/2. Right? That is a lot nicer to deal with than trying to set up the epsilon proof. Okay, we can also use, so that's using this exercise. So this is exercise 2. Let me see what it was again. 2.3.10. But I also wanted to show you that we can use the algebraic limit theorem. Okay, so we can also use the algebraic limit theorem, because when we start, so with, say, I'm looking at the limit of n over the 2n plus 4. Okay, what we do, is by the algebraic limit theorems, we can move the limit to the top and the bottom of the fraction and distribute it. But what I want to do first is I'm going to multiply the top and the bottom by 1 over n. I'm taking the highest power of n in the denominator to do that. And you'll see hopefully in a second why I want to do that. Okay, and when we distribute that across, the numerator will just become 1. The denominator will become 2 plus 4 over n. And now we can use the algebraic limit theorem, because this, the limit of this whole thing, and here's where the algebraic limit theorems come in. This will be the limit of 1 over the limit of 2 plus the limit, and actually let me do it this way, plus 4 times the limit of 1 over n. So this uses basically almost all of the algebraic limit theorems, the one with the fractions, the one with the sums, the multiplications, okay, the Really, this was the constant multiplication rule. Okay, so, and from here, well, the limit of 1, is just 1. The limit of 2 is just 2. Okay, plus 4. Now times the limit of 1 over n. Well, we know that 1 over n goes to 0, so that zeroes out, and we get 1/2. Okay, so either with this new exercise we just looked at, or with the algebraic limit theorem, hopefully you see how much easier it can be to find or to prove that these limits go to where we think they should go. And it keeps us from having to do it the long way with an epsilon proof. Okay, we should still know how to do that because there are cases where we will still have to fall back on that. However, these two techniques I find a lot friendlier in practice for the most part. Okay, so now I think we're ready to move to section 2.4, which is on the monotone convergence theorem. And this is going to give us the condition that I mentioned in the previous lecture, that just being bounded is not enough to guarantee that a sequence converges. We need other conditions on top of that. And the first one is, well, if it's, say, increasing and bounded, then it has to converge. Or if it's decreasing and bounded below, then it has to converge. Okay, so let's first give official definitions for those and talk about what we mean by monotone. Okay, so this one shouldn't be, all that tricky. A sequence AN is increasing if AN is less than or equal to AN plus 1 for all n in the naturals, of course. It's decreasing if AN is greater than or equal to AN plus 1 for all n in the naturals. Okay, hopefully nothing brand new there. And we say that a sequence is monotone if it is either increasing or decreasing. So monotone is just a catch-all for either. If it's increasing over its entire life or it's decreasing over its entire life. Now notice we are saying for all n in the naturals. So we would not say that a sequence is monotone if it changes from increasing to decreasing. So the sequence here increases for a little while, then decreases, then increases, and decreases, then increases. This is not monotone. Okay, but this sequence, say that's always decreasing, this is monotone. Now I always think of it, if you think of people who are monotone, sort of like Bill Stein, I think that was his name, Bill Stein. Things that are monotone are kind of boring typically, and a monotone sequence is actually kind of boring because, well, it's always behaving the same way. It's not doing anything interesting like this guy here is. Instead, it's always just sort of, going about its business just the same way over and over and over again. Okay. All right, so that is the definition of monotone. Now, let's talk about the monotone convergence theorem. All right, so here's the monotone convergence theorem, abbreviated as the MCT. If a sequence is bounded and monotone, then it converges. So there is the extra condition that we need. If a sequence is both both bounded and monotone, then it converges. So here's why this is. Okay, if you think about it in terms of a function, so if you are drawing it on a xy plane here, all right, and say that the sequence is bounded by m And we know that it is always increasing. So, it might, who cares where it starts? It could start here. But if it's monotone, that means every next step of the sequence has to live above the previous one. Okay? And even if we have a pretty steep jump at some point, eventually, if it is going to be both bounded and monotone, then the only way we can make that happen is if it gets closer and closer to this line and essentially gives us a horizontal asymptote. Because if we jump, so if I jump above this line, well then the sequence is no longer bounded. And if I start to go down, well then it's no longer monotone. So the only way that this can actually happen is if the sequence converges, and it seems, just based on the picture, the only way this can happen is if it converges, and it converges to, say in this case, its supremum, the least upper bound. Okay, and you can do the same thing if the sequence is decreasing and bounded below. All right, if I wanted to do it in terms of just the number line instead, if I know that my sequence is bounded above and I know that it's increasing, well again, on the number line, I can get closer and closer to this bound, but eventually these points have to get closer and closer together, and we would have to start zooming in, right? We'd have to start zooming in to then see, okay, we're getting closer and closer and closer and closer once again. All right, so again, the only way you can be both bounded and monotone is if you're converging to that least upper bound. So the idea is a sequence can only be increasing and bounded above if it converges. And specifically, converges to the least upper bound. All right, so when we go to prove this, this is the idea we're going to use. We're going to use the fact that the sequence must be converging to its supremum. All right, so when we start tackling this proof, it may be a good idea to go back and look at some of those important theorems we had about supremums, because there's one in particular that we are going to utilize. Okay, so let's get to it. All right, to start with, since I already know, well, maybe I don't already know it, but based on my pictures and thinking about it, I suspect that the sequence of this type is going to be approaching its supremum. Now, we are assuming, so assume that the sequence, let's call it AN, is increasing and bounded. The case where AN is decreasing is very similar. Okay, so the case where AN is decreasing is very similar. In fact, we could probably do it without loss of generality here. Okay, so now, since I want a supremum, so now that I know AN is increasing and bounded, I know that I'm going to want to talk about the supremum, right? So that means I need to set up a set, right? Because soups act on sets. So I'm going to let, actually, let me let capital A be the set of all ANs for n's in the naturals. All right, so I'm just making a set out of my sequence, which is okay. We can do that because remember, sets just go ahead and automatically ignore repeats, but we shouldn't have any repeats. Well, we actually might have some repeats, but we shouldn't have too many because we're increasing here. All right, hopefully we don't have that many. Now, since the sequence AN is bounded, this implies that the set A is bounded. It's both bounded above and below. Now I'm going to put a star next to that. And I want, if you don't believe me on that, okay, I want you to go back and look at what it means for the sequence to be bounded, what its definition is, and then how that actually implies that the set A is bounded both above and below. Okay, because when we say that A is just bounded without a condition, it means it's both bounded above and below. Okay, so if you're unsure about that, give it a think and take a look at those definitions and convince yourself that this statement is true. Okay, so therefore, we'll call S equals the supremum of A exists. And this is by the AOC, right? The axiom of completeness. All right. Now, here's where we're going to use one of our important theorems regarding supremums. All right, and that's limit, or I'm sorry, not limit, but lemma 1.3.8. Okay, so now I'm going to let epsilon be greater than 0. Then we know that S minus epsilon is not an upper bound of A, and there exists an AN in A such that S minus epsilon is less than AN. So this is where I'll say C lemma 1.3.8. I'm sure you remember we used this lemma a lot when we were doing the supremum stuff. Okay, so I'm going to let epsilon be greater than 0, then S minus epsilon is not an upper bound, and there exists an AN in capital A such that S minus epsilon is less than AN. Okay, so let's choose capital N in the naturals such that this capital N is the one that satisfies this. So such that S minus epsilon is less than A sub capital N. Okay? Then, for all little n greater than or equal to this big N, we have this. That s minus epsilon is less than an, which will be less than or equal to a sub n. So for every next n, right, that an is going to be greater than or equal to this particular n, and that's because an is increasing. Okay? So that's where this piece here comes from. This is the increasing part. Right? Because every higher n, the value of a will be greater, right? It's increasing. All right? So then, by definition of supremum, so I'll just say by definition, we have that s minus epsilon is less than a sub capital N, which is less than or equal to a sub n, little n, which is going to be less than or equal to s, right? This is because s is the supremum. And then this s is strictly less than s plus epsilon. That's just because we're adding a positive number to the s. Okay, and this is true for all little n greater than or equal to the capital N. Okay, so this may seem a little rough. I'm only going to pick out the pieces that I really care about. Specifically, I'm going to take the s minus epsilon, the a sub n, and the s plus epsilon. So this implies that s minus epsilon is strictly less than a sub n, which is strictly less than s plus epsilon. I'll just say for all little n greater than or equal to capital N, which implies, well, now I'm going to subtract s throughout. So this implies that negative, actually, I'm not going to do that. What I'm going to do is that this implies that a sub n is in the open interval s minus epsilon to s plus epsilon. And this is the epsilon neighborhood around s. And this is for all n greater than or equal to capital N. And we've got it. Okay? This is from our set definition. And you saw me, I almost went to the distance one, but I saw actually that the set definition would be faster here. So that's why I went with that. So that's actually what we wanted to show. We wanted for all epsilon, right? So for any epsilon greater than 0, we found an n such that for all n greater than this capital N, every term of the sequence is in the epsilon neighborhood around s. So this implies that an converges to s. Okay? In other words, an converges to the supremum of all the an's. Okay? And that ends the proof. Okay, so it's not just that if you're increasing and bounded as a sequence, you have to converge. You converge to your own supremum, essentially. Okay, so that is the extra condition we need. So we can't just have bounded. We have to have bounded and increasing, or decreasing and bounded below. So I'll say that if an is decreasing and bounded, then it's not that A goes to the supremum anymore. An will actually converge to the nth. So if it's decreasing and then bounded below, the only way it can always be decreasing and also be bounded is if it converges to its infimum. All right, I want to take a minute to talk about why the monotone convergence theorem is so important and why theorems like it are so important. And that's why what we'll be focusing on really for the remainder of this chapter. And so the reason why the monotone convergence theorem is so important is because up until now, we needed to know what the limit was. To prove convergence. Right, because remember, we were always wanting to show that the absolute value of an minus a is less than epsilon, but we can only do that if we know what the a is. Right, we have to know what that a is to put it in there to even get started on the epsilon proof. Okay, so what the monotone convergence theorem allows us to do, right, this allows us to prove convergence even if we don't know the limit. And in fact, it's only the first such theorem that helps us with that. Okay, so let me show you an example of how this works. Okay, so consider this theorem, or sorry, not this theorem, but this sequence. So it's defined recursively, so x sub 1 is 3, and x sub n plus 1 is equal to 1 over 4 minus x sub n. Okay, and I want to prove that the sequence x sub n converges. And then we'll go even crazier and find what it converges to. Okay, well, I don't have a lot to go on here, and seeing as this section's all about the monotone convergence theorem, it's likely we need to use the monotone convergence theorem. So can we prove that xn is bounded and monotone? Okay, well, let's look at what we get if we start plugging some values in. So x1 is 3, Then x2 is going to be 1 over 4 minus 3, which is going to be 1 over 1, so that's 1. Then x3 is going to be 1 over 4 minus 1, which is 1/3. Okay, and then x4 will be 1 over 4 minus 1/3. Right, which will equal 1 over, will that be 12/3 minus 1/3, which is 1 over 11/3, which is 3/11. Okay, and then x sub 5 will be 1 over 4 minus 3/11, which will be 1 over, what will that be, 44 over 11 minus 3/11, which will be 1 over 41/11, which is 11 over 41. Okay, now this, of course, looks kind of bad, but x sub 3 here, that's 0.333 repeating. 3 over 11 ends up being 0.27 repeating. 11 over 41 is 0.268 29. It looks like well, it's hard to see what actually repeats there, but it's approximately that. So it looks like x is decreasing. Okay, and possibly bounded. It's definitely bounded by above, just automatically, since it's decreasing, and possibly bounded below. So let's try and prove this. So, okay, so let's start by showing that xn is bounded. Now, a good candidate for that is going to be, maybe 3, right? Because let's show that xn is bounded by showing that the absolute value of xn is less than or equal to 3 for all n in the naturals. And this is the same thing as showing that xn is trapped between -3 and 3. Okay, so we have that this is true for x1 and x2 and x3. Okay, so these can count as our basis step. And from here, our induction hypothesis, because for this we do have to use our good friend induction, is that we suppose that xn is trapped between -3 and 3 for some n in the naturals. Okay, then we want to show it for xn plus 1. Okay, now remember the formula for xn plus 1 is 1 over 4 minus x sub n. So maybe we can manipulate this to get it to look like this, or we can just use, say, this formula here. Okay, so I'm going to try and get it to maybe look like this. So let's, I'm going to start by, I'm going to take this and I'm going to multiply it all through by -1. So I'll get 3 is greater than or equal to negative x sub n, which is greater than or equal to -3. Well, that should make some sense, because if xn is trapped between -3 and 3, it's negative will be as well. Okay. Now I'll add 4 to both, or all 3 pieces. So I'll get 7 is greater than or equal to 4 minus x sub n, which is greater than or equal to 1. Okay. Now, since this is all nice and positive, I can just flip all the fractions over. But when I do that, remember, I have to flip the signs. So I'll get that 1/7 is less than or equal to 1 over 4 minus x sub n, which is less than or equal to 1. And thankfully, 1 is less than 3, and 1/7 is greater than -3. Okay, and this is the formula for x plus 1. So this implies that -3 is less than or equal to xn plus 1, which is less than or equal to 3. So xn plus 1 absolute value is less than or equal to 3. So by induction, the sequence xn is bounded. Now note, this probably is not the least upper bound, because as you see here, when we were doing this, we got like 1/7 and 1 here. So it's possible that, you know, we have a better lower bound that we could find, but that doesn't really matter. We just need to show that it is bounded. Okay, so now let's try and show that it is decreasing. Okay, so we've already taken care of the basis step, right? Because x1 is greater than or equal to x2, which is greater than or equal to x3, which is greater than or equal to x4, which will be our basis step. Okay, so for the induction hypothesis, all right, suppose that xn is greater than or equal to xn plus 1 for some n. Okay, then I'm going to try basically what I did last time. I'm going to negate everything. Now I know that both of these are less than, or they're trapped between -3 and +3. Whoops, and it should be this way. I probably wasn't smart to reverse my inequalities here, but it'll work out. All right, so I can negate it all. So I have -3 is less than or equal to -xn, which is less than or equal to -xn plus 1, which is less than or equal to 3. All right, then sort of running out of space here, but then I'll add 4 to everything. So I'll get 1 is less than or equal to 4 minus xn, which is less than or equal to 4 minus xn plus 3, which is less than or equal to 7. Now, if you're looking at this and thinking, well, could we have proved that it was bounded and decreasing all in one go? The answer is probably. Sometimes there are slick ways to do this. Okay, so then, now I'll flip everything over. And remember, we can only do that if it's positive. It's all positive. And we flip the signs. So now we have that 1 is greater than or equal to 1 over 4 minus xn, which is greater than or equal to 1 over 4 minus xn plus 1, which is greater than or equal to 1/7. And there we go. This is xn plus 1, which I've now shown is greater than this, which is the definition of xn plus 2, and that's what we wanted to show. Okay, so now we've proven that xn converges. But the question is, what does it converge to? Okay, and we can figure that out as well. The first thing I want to mention is if, so I'll star this, if xn converges to L, then xn plus 1 also converges to L. Okay, hopefully this makes sense. All we're doing with xn plus 1 is we start counting at 2 instead of 1, right? We'll go 2, 3, 4. So we're always just a step ahead of this one, but if this one converges, then so does this one. This one's just one step ahead. And when we're talking about infinities, being one step ahead is really not anything to be proud of, right? So then, on top of that, since limits are unique, if this sequence is always equal to this sequence, then the limit of xn plus 1 will equal the limit of 1 over 4 minus xn. And this is a result of the algebraic limit theorem and the ordering theorem, all these other things, and the fact that limits are unique. All right, and we know that the limits exist because, well, we've proven that xn converges thanks to the monotone convergence theorem. Okay, so if xn converges to L, then this limit is equal to L. And this limit, well, again, we can bring the limit up and that will go to 1 on the top. This will go down, the limit of 4 is 4, and then the limit of xn is L. Okay, so then from here, this is also from the algebraic limit theorem. And now we can solve for L to figure out what xn converges to. So we'll multiply this across to get 4L minus L squared is equal to 1. And then I'll actually be easier to move things over to this side because we'll get L squared minus 4L plus 1 is equal to 0. Okay, and then it doesn't really look like this will factor, so I'm going to use the quadratic formula here. L is going to be a negative b, so that will be 4 plus or minus the square root of b squared, 16, minus 4ac, so a and c are both 1. Okay, and that's going to be all over 2a. All right, so we'll get 4 plus or minus the square root of 12, which we can take, that's 4 times 3, so we can take a 4 out of that. Or, I'm sorry, a 2 out of that. All right, so we'll get 2 plus or minus the square root of 3 all over 2. Now, which one is our sequence going to? And I just realized I made a mistake here. That 2 should cancel away. Okay, so if we look at a calculator, 2 plus square root 3 is about 3.73, and then 2 minus square root 3 is about about 0.2679. Okay, and now if you were to check this recursive relationship and go out maybe 10, like if you take x out to 10 and figure out what that is, and then check it against 2 minus root 3, you'll get what looks almost the same thing. We know it can't be this one because every term in our sequence is less than 3. So it can't be this one, so it's got to be this one. So something interesting here is notice that every xn is a rational number. However, xn converges to 2 minus root 3, which is in the irrationals. Okay, now that is a very interesting fact there that we are going to look at in more detail as we go further. But this is essentially telling us that the rationals are not closed under limits, but the reals are. Okay, I think that's probably enough brain melting for one day. So I will catch you all on the next one. Cheers.